Welcome! Today, we're going to explore electrochemical methods which are powerful and widely used tools in analytical chemistry. These methods rely on measuring electrical signals such as voltage, current, and charge that arise from chemical reaction happening in an electrochemical cell. Specifically, the study redox reaction where electrons are transferred between chemical species at the surface of electrodes emerge in a solution. Electrochemical methods are popular because they are highly sensitive, fast, and cost-effective, making them ideal for detecting and measuring chemicals in a variety of samples. You might already be familiar with some common examples like pH meters that measure acidity or sensor that detects drugs and environmental pollutants. In this chapter, we focus on electrochemical techniques where the analytical signal comes from the potential current or charge in the electrochemical cell. Although there are only three basic types of electrochemical signals, there are many different experimental designs and methods built around these signals. So many that it is impossible to cover them all in one introduction. To simplify, we can divide electrochemical techniques into two main categories: bulk techniques and interfacial techniques. Bulk techniques measure properties of the entire solution in the cell. For example, conductometry measures the solution conductivity, which depends on the total concentration of dissolved ions. On the other hand, interfacial techniques focus on the interface between the electrode and the solution. Here, the potential current or charge depends on the specific chemical species present right at the electrode surface. Measuring pH with a glass electrode is a classic example of an interfacial electrochemical method. In this lesson, we will focus on electrochemical techniques because they provide detailed information about specific analytes. Now, a little bit of basic concept and analogy. To understand how this method works, think of it as electrochemical cell like a tiny battery. Just like a battery produces electricity through chemical reaction, electrochemical cells generate electrical signals when chemical reaction happens at the electrodes. We measure things like voltage, current, or charge, and these measurements tell us about the chemicals in the solution. This connection between chemistry and electricity is what makes electrochemical methods so powerful for analysis. Electrochemical analysis has a rich history. It started with early discoveries about electricity and chemistry 100 years ago. In the 80s, scientists learned how to split water using electricity. Later, the invention of the three electrode system allowed more precise measurement. A big milestone was the development of polarigraphy in the 1920s, which earned a Nobel Prize. Today, we use tiny electrode and advanced materials to make these methods even more sensitive and selective. There are several main electrochemical techniques used in analytical chemistry. Potentiometry measures the voltage without passing current like in pH meter or ion selector electrodes. Next is voltammetry, measures current while changing the voltage, which helps detect small amounts of drugs or pollutants. Next is colorimetry, measures the total charge passed during a reaction, useful for precise quantification. Next is conductometry, measures how well a solution conducts electricity, which tells us about ion that is present. Next is electrochemical impedance spectroscopy, or EIS, looks at how the system resists electrical flow at different frequencies, helping study batteries or corrosion. Each technique gives us different information about the chemical samples. Now, the electrochemical methods are used in many important areas. First is in environmental science. They detect heavy metals and pollutants in water and soil. Next is in pharmaceuticals. They help measure drugs levels accurately. In medicine, they are behind glucose meters and rapid disease tests. In energy research, they help improve batteries and fuel cells, and new wearable sensors use this method to monitor health in real time because they are sensitive, fast, and affordable. Electrochemical methods are essential tools in analytical chemistry today.
Potentiometric methods, a key subtopic of electrochemical analysis, involve measuring the electrical potential of a solution using electrodes to determine ion concentrations without drawing significant current. This technique, rooted in the Nernst equation, is widely used for pH measurement, potentiometric titrations, and environmental monitoring, offering high precision in chemical analysis. Potentiometry is an electrochemical technique that measures the electrical potential or voltage of a solution using specially designed electrodes. This potential difference arises due to ion activity in the solution, allowing scientists to determine concentrations of specific ions, particularly pH levels, without altering the sample. Unlike traditional titrations, which rely on color changes from chemical indicators, potentiometry provides highly accurate, objective results by directly detecting electrochemical reactions through electrode interactions. This method is widely used in analytical chemistry, environmental studies, pharmaceuticals, and food quality control, ensuring precise measurements across various industries. Potentiometry operates on the Nernst equation, a fundamental principle in electrochemistry that establishes a relationship between electrode potential and ion concentration. This equation enables scientists to predict how the voltage of an electrochemical cell changes based on the concentration of specific ions in solution. To perform potentiometric measurements, there are two electrodes required. So first, we have the indicator electrode. This electrode interacts with ions in the solution and changes potential based on their activity, helping to determine the analyte concentration. Second, we have the reference electrode. It provides a stable and known potential, ensuring that any observed voltage changes are due solely to the sample being measured. The electromotive force generated between these electrodes is then recorded and analyzed. Since EMF is directly linked to the ion concentration, scientists can precisely determine unknown values without relying on chemical indicators or visual changes, making potentiometry a powerful tool in analytical chemistry. Potentiometric methods have a wide range of applications, making them indispensable in scientific and industrial settings. First, we have pH measurement. It is one of the most common uses. Potentiometry is employed in laboratories to determine the acidity or alkalinity of solutions with high precision. Second, we have the potentiometric titration. This technique is used to determine the concentration of unknown substances by monitoring voltage changes during a titration process. Third, we have environmental analysis. Potentiometric sensors help detect pollutants and contaminants in water samples, ensuring safe drinking water and monitoring industrial waste. Fourth, we have the pharmaceutical and food industries. Quality control processes in these industries rely on potentiometric methods to verify the composition and purity of products. For example, potentiometry is used in drug formulation to ensure precise pH levels and in food production to test acidity levels in beverages and processed goods. These applications highlights the versatility of potentiometry in delivering accurate, reliable, and non-invasive chemical measurements across multiple fields. Potentiometry offers several key advantages that make it a preferred method for chemical analysis across various industries. First, we have highly accurate. Unlike traditional colored-based indicators, potentiometric measurements rely on electrical potential, providing precise and objective results. Second, works in turbid or colored solutions. Many chemical analysis methods struggle with solutions that are murky, colored, or opaque. Potentiometry overcomes these limitations as electrode measurements are independent of visual appearance, making it ideal for complex sample analysis. Third, can be automated. Modern laboratories and industries integrate automated potentiometric system into analytical instruments for continuous monitoring. This reduces human error, enhancing efficiency and ensure high-speed real-time analysis. Fourth, applicable across industries. Potentiometric techniques are widely used in various fields, including pharmaceuticals, drug formulation and quality control, food industries, acidity measurement and beverages, environmental science, water quality testing, and medicine, electrolyte balance monitoring. These advantages make potentiometry an essential tool for accurate, efficient, and versatile ion analysis, ensuring quality and reliability in scientific research and industrial process. For our conclusion, potentiometry is an essential electrochemical technique that allows for highly accurate ion concentration measurements by analyzing electrical potential changes in a solution. Its precision and reliability make it a fundamental tool in both scientific research and industrial processes, helping laboratories determine pH levels, perform titrations, and analyze environmental samples. With its fast and efficient approach, potentiometry has become a widely used method across industries such as medicine, food production, pharmaceuticals, and environmental science, ensuring quality control and advancing analytical chemistry.
For the colorimetric overview, colorimetric is a electroanalytical technique that measures the amount of analyte in a sample by determining the quantity of electricity and columns needed to completely oxidize or reduce it. So this method is based on Faraday's law of electrolysis, which states that the amount of substance transformed is directly proportional to the quantity of electricity passed through the electrochemical cell. So in simple terms, colorimetry measures how much electricity is used to completely change the chemical state of the substance being analyzed. So the next slide, we have the completion of the reaction is indicated by the decrease in the current to zero. So this can be measured by the colorimeter. So colorimetry measures concentration by completely converting the analyte from one oxidation state to another using a precisely controlled amount of electricity. So next slide, let's talk about the gradually refinement of colorimetric. So the colorimetric methods developed wasn't a single discovery, but a gradual evolution building upon fundamental electrochemical principles. While pinpointing an exact discovery is difficult, there are key milestones included in our PPT. So we have there an early contribution in pre-1938. So Michael Faraday's law of electrolysis, established in the 1830s, laid the groundwork. His work demonstrated the direct proportionality between the amount of substance transformed during um, electro, electrolysis and the quantity of electricity passed. So this fundamental relationship is the core of colorimetry. colorimetry. So early applications such as growers' use of surface colorimetry in 1917 to assess thinned copper wire or contributed to the method's practical development. So for the formalization of the term in 1938, the term colorimetry itself was introduced in 1938 by the Hungarian chemist Laszlo and Zoltan. Their work formalized the technique and helped establish it as a distinct analytical method. So for the growth and refinement in mid-20th century, colorimetric methods saw widespread use in the mid-20th century. So N. Howell Foreman's work recognized with the Palladium Medal in 1957. So it highlighted the techniques high precision and accuracy, especially at low concentrations. So, however, the rise of volumetry, and other analytical techniques later reduced its prominence, although certain certain application like Carl Fisher titration remained highly relevant. So in summary, no, colorimetri's emergence wasn't a singular event, but a process involving Faraday's foundational work to formalization to the technique by the two Hungarian chemists and subsequent refinement and application throughout the 21st century. So the method continues to evolve with a modern advancement in instrumentation and application. For the next slide, the main principle of colorimetry centers around measuring the quantity and electricity directly proportional to the chemical reaction occurring at the electrode. So this relationship is defined by Faraday's law, expressed by the equation na ito makita sa slide, and there makita nato ang Q. Q represents the quantity of electricity in coulombs, and N signifies the number of electrons transferred per mole of analyte. So the F denotes Faraday's constant, which approximately 96,487 coulombs per mole. So the Na represents the number of the moles of the analyte. So in essence, no, colorimetry uses the precise measurement of electricity to determine the amount of analyte percent. So relying on the fundamental relationship between electrical charge and the chemical changes at the electrode surface.
Good afternoon, everyone. Today, I'll be discussing colorimetric methods, a powerful analytical technique used to determine the amount of a substance by measuring the quantity of electricity needed to completely oxidize or reduce it. This technique offers high accuracy and precision, making it valuable in various fields. But I will be focusing on the two primary types of colorimetry and highlighting their application and significance. So the first type of colorimetry is colorimetry at constant current, or called as amperostatic or copometric titration. It is an electroanalytical technique where a constant current is applied to an electrochemical cells. This constant current forces a redox reaction to occur at the working electrode. The reaction continues until the analyte is completely oxidized or reduced. The key measurement is the time it takes for this complete reaction to occur. So, imagine a scenario where we apply a constant electrical current to an electrochemical cell containing our analyte. So the current flows until the analyte is completely consumed in a redox reaction. We carefully measure the times it takes for this complete reaction. Knowing the current and the time, we can use the Faraday law to calculate the exact amount of analyte present. This is because Faraday law directly links the quantity of electricity, which is the current times time, to the number of mole of electrons transfer, and thus to the moles of analyte. So this method is relatively straightforward and quick, making it suitable for routine analysis. A common application is the determination of water content in various samples using Carl Fisher titration, a classic example of a constant current colorimetry. So, naaday advantage ug disadvantage ang colorimetry at constant. So, ang advantage is the first is relatively simple and inexpensive instrumentation. So, dili siya mahal. So, second one is faster analysis compared to constant potential colorimetry. And the third one is suitable for routine analysis. Mao na siya ang iyahang mga advantages. So, napod siya at disadvantages, which is less selective than constant potential colorimetry or any electroactive species present at the working electrode potential will react. So, requires precise control of the current o kuan po, not suitable for analytes with slow reaction kinetics. So, in summary, constant current colorimetry is a straightforward technique useful for determining the amount of analyte by measuring the time required for complete electrolysis at a constant current. Its simplicity and speed make it suitable for routine application, but its slower selectivity limits its use in complex sample. So the second type of colorimetry method is controlled potential colorimetry, also known as potentiostatic colorimetry. It is a highly selective electroanalytical technique used to determine the amount of a substance by measuring the quantity of electricity or the charge required to completely oxidize or reduce it at a precisely controlled electrode potential. So in this method, a constant potential is applied to the working electrode. This potential is selected to be sufficiently positive or negative to ensure that only analyte of interest undergoes oxidation or reduction. The current flowing through the cell decreases exponentially as the analyte is consumed, eventually approaching zero when the reaction is complete. The total charge passed during the electrolysis is measuring using an integrator, and this charge is directly proportional to the amount of analyte present. This method offers high selectivity because only the analyte at the chosen potential will react. Instead of a constant current, we maintain a constant potential at the working electrode. So electrolysis occurs and the current gradually decreases as the analyte is consumed. We use an integrator to measure the total charge passed during the electrolysis. Again, using Faraday law, we can calculate the amount of analyte. This method is more selective because of only species that can be oxidized or reduced at the applied potential will react. This improves accuracy by minimizing interference from the other substances in the sample. This technique used to determine the concentration of specific metal ions in solution or analyzing trace elements in the environmental sample. So the advantages of constant potential is high selectivity due to the controlled potential of accurate quantification and suitability for analytes with slow reaction kinetics. So the disadvantages is requires more sophisticated instruments such as a potentiostat and an integrator, and can be slower than controlled current colorimetry. So let's proceed to the application of colorimetric methods. So the first one is the inorganic analysis. So the colorimetry is used to determine the amount of inorganic substances such as ions in a sample. So this is achieved by measuring the quantity of electricity, which is the charge required to completely oxidize or reduce the target ion. The principle relies on Faraday's law, which states that the amount of substance transformed is directly proportional to the charge passed. So how it works? A sample containing the target inorganic ion is placed in an electrochemical cell. A control potential or a current colorimetry is applied, causing the ion to undergo a redox reaction, either oxidation or reduction. So the total charge consumed during this reaction is precisely measured. This charge is then directly related to the number of moles of the target ion present using Faraday's constant. So, the importance of inorganic analysis is in a various field. For example, determining the concentration of heavy metals such as lead, cadmium, mercury, and etc. in water samples is vital for environmental monitoring and public health. Similarly, precise determination of metal content in alloys is crucial for quality in metallurgy. So the colorimetry offers high accuracy and selectivity, making it a preferred technique for this application. So the second one is the analysis of radioactive materials. So colorimetry is used to determine the amount of specific radioactive isotopes in a sample. The high accuracy and sensitivity of colorimetry are particularly important when dealing with radioactive materials, where precise measurements are critical. So how it works? So similar to inorganic analysis, colorimetry measures the charge required for a redox reaction involving the radioactive isotopes. However, special precautions are necessary due to the hazardous nature of the samples. Small sample sizes are typically used to minimize radiation exposure. So, what is the importance of analysis of radioactive materials? So, accurate measurement of radioactive isotopes is crucial for nuclear safety, environmental monitoring, and nuclear waste management. So, colorimetry's precision helps ensure safe handling and disposal of radioactive materials, preventing environmental contamination and protecting human health. So, for example, determining the amount of plutonium in a spent nuclear fuel sample, a controlled potential is applied, causing a redox reaction involving plutonium. The charge consumed is directly proportional to the amount of plutonium present. So the third one is the microanalysis. Colorimetry is used to analyze extremely small samples or microsamples. The technique's high sensitivity allow for accurate measurement even when only trace amounts of the analyte are available. So how it works? The procedure is similar to other colorimetric techniques, but the sample size is significantly smaller. Specialized microelectrodes might be used. So, what is the importance? The microanalysis is crucial in fields like forensic science, where only tiny amounts of evidence might be available. Colorimetry allows investigator to obtain reliable quantitative results from limited samples, providing crucial information for criminal investigation. For example, determining the amount of a specific drug in a trace amount of blood found at crime scene. So the last one is the electrolytic determination of organic compound. So colorimetry can be used to determine the quantity of specific organic compounds. This often involves a controlled potential or controlled current electrolysis to oxidize or to reduce the organic compounds. So, a controlled potential or current is applied to the electrochemical cell containing the organic compound. The compound undergoes a redox reaction and the charge consumed is measured. This charge is then directly related to the amount of the organic compound present. This method is valuable for determining the purity and concentration of specific organic compounds in various applications, such as pharmaceutical analysis, food analysis, and environmental monitoring. For example, determining the concentration of ascorbic acid or vitamin C in a fruit juice sample. A control potential is applied, oxidizing ascorbic acid. The charge consumed is directly proportional to the amount of ascorbic acid present. So, in summary, colorimetric is a versatile technique with applications across diverse fields, providing highly accurate and precise quantitative analysis in various scenarios. Its ability to handle small samples and its high sensitivity make it special valuable in microanalysis and the analysis of hazardous materials.
Voltammetry is a way scientists can study chemicals. They can find out what chemicals are in a sample and how much of a chemical is there. It's like being a chemical detective using electricity to find clues. So, how did this voltammetry do its magic? Well, it all has to do with electricity and chemical reactions. Imagine you have a solution like water with some stuff dissolved in it. We want to know what that stuff is. So, with voltammetry, we put special metal pieces like called electrodes into the solution. Then we carefully change the electrical voltage applied to one of these electrodes. As the voltage changes, some chemicals in the solution might react. They might gain or lose tiny particles called electrons. So these movements of electrons it is an electric current. So the key idea is that different chemicals react to a different voltages. A certain voltage will make a specific chemical react. When that chemical reacts, it creates a current. We can measure this current. The amount of current tells us how much of that chemical is present. The story starts in an early 20th century. A very smart scientist from Czechoslovakia named Jaroslav Hirovsky was working on something new in 1922. He invented a technique called polarography. This was the very first type of voltammetry. So Professor Jaroslav Hirovsky used a special electrode made of dropping mercury. As tiny drops of mercury fell, he applied a change voltage and measured the current. This was a huge breakthrough for chemistry at that time. For this incredible invention, Jaroslav Hirovsky won the Nobel Prize in Chemistry in 1959. Over the years, scientists kept working to make voltammetry even better. They realized that mercury, yes, while useful, it also had some limitations. So researchers started to develop different kinds of electrodes. They used solid materials like platinum, gold, and carbon. So these new electrodes open up many more possibilities. So how does voltammetry works? Let's imagine we're on an experiment. Of course, we first need to set up our experiment, right? The heart of the set is an electrochemical cell. This usually involves a small container like a beaker. Inside the beaker, we put our sample solution. This is the liquid we want to analyze. Then we carefully place three special electrodes into the solution. There is the working electrode where the main chemical reaction happens. Then there is a reference electrode which keeps the voltage stable. And there is the counter electrode which complete the electrical circuit. Once our cell is all set up with the solution and electrodes, we connected to a machine. So this machine is called the potentiostat. So potentiostat controls the electrical potential or voltage that is applied to the working electrode. It can change this voltage very precisely. The way the voltage change depends on the specific type of voltammetry we're doing. Okay, depends on the voltammetry what we are trying to do in this experiment. For example, as the potentiostat changes the voltage of the working electrode, things starts to happen to the solution. Okay, if the voltage reacts just the right level of for a particular chemical, that chemical will react also. It has tons of practical applications. One really important area is environmental monitor. So scientists use this voltammetry to check for pollution in our water and soil. For example, it can detect one tiny harmful heavy metals like lead or mercury. So these metals can be very dangerous even in small quantities. So voltammetry helps us make sure our working water is safe. It also helps find pollution sources and clean up our environment. Voltammetry is also a star in the world of medicine and healthcare. It can be used for medical diagnostics. Doctors and researchers can use it to measure important substances in biological samples like blood or urine. For instance, some voltammetric centers can measure glucose levels for people with diabetes. Others can detect certain drugs or their breakdown products into the body. This helps the doctor diagnose the diseases, monitor a patient's conditions, or make sure medications are working correctly.
So good day everyone. I'm gonna tackle about the amperemetric method. So what is amperemetric method? It is an electroanalytical technique that measures the current produced during the electrochemical oxidation or reduction of an analyte at an electrode under a controlled potential. This method is widely used in various fields due to its sensitivity and ability to detect low concentrations of substances. The measured current is directly proportional to the concentration of the analyte, making it a valuable tool for quantitative analysis. So the development of amperemetric method. The first one in early stages, amperemetry roots can be traced back to the late 19th century when early researchers began exploring the relationships between electrical current and reactions occurring at electrodes. Michael Faraday's works on electrolysis provide a framework for understanding these reactions. Second, the polography. In the 1920s, Jaroslav Hayrovsky developed a polography, which allowed for the measurement of current as a function of applied potential. This technique paved the way for conventional amperemetric techniques. Third one is the single potential amperemetry. This method involved applying a constant voltage between two electrodes and measuring the current. It was used for detecting electrochemically active ions like cyanide, sulfide, and iodide. Fourth one is the pulse amperemetry. To address the issue of electrode fouling, pulse amperemetry was developed. This technique involved applying a series of voltage pulses to the electrode, enhancing sensitivity and allowing for the detection of fast responding analytes. And lastly, the amperemetric biosensors. In recent years, amperemetric biosensors have gained prominence. These sensors combine carbon electrodes with enzymes or other biomolecules to detect specific analytes like glucose or amino acids. So step-by-step process of amperemetric experiment. The first one is prepare the electrochemical cell. Set up a 3-electrode system with a working electrode, a reference electrode, and an auxiliary electrode. Second, add the electrolyte solution. Introduce a solution that contains the analyte and supporting electrolyte to ensure good conductivity and minimize migration currents. Third, apply the potential. Set the working electrode potential at a value where the analyte will undergo oxidation or reduction. This potential should be optimized to maximize the response for the analyte of interest while minimizing interferences. Fourth one is the measure the current. Record the current flowing between the working and auxiliary electrodes. This current is directly proportional to the concentration of the analyte. And lastly, the calibration. Create a calibration curve using standard solution of known concentrations to quantify the analyte concentration in the sample. Practical applications of amperemetric method. Amperemetry has a wide range of applications across various fields, including first one is the blood glucose monitoring. Amperemetric biosensors are used in blood glucose monitors to measure glucose levels in real time. These devices use carbon electrodes coated with glucose oxidase and a mediator like ferrocene to detect glucose concentration. Second, the neurotransmitter detection. Amperemetry is used in electrophysiology to study the release of neurotransmitters from cells.
Carbon fiber electrodes are placed near cells to detect the oxidizing neurotransmitters released into the medium. Third one is the environmental monitoring. Amperometric sensors are employed to monitor pollutants and environmental samples. They can detect substances like oxygen, hydrogen peroxide, and other electrochemically active species. Fourth one is the food safety. Amperometric methods are used to analyze food samples for the presence of harmful substances. They can detect contaminants like pesticides and foodborne pathogens. And lastly, the pharmaceutical analysis. Amperometric titrations are used to assay pharmaceutical substances like procrastinamide, hydrochloride, and nickel salts. These titrations provide accurate and precise measurements of drug concentrations. In summary, amperometry is a versatile and sensitive electroanalytical technique with applications spanning clinical diagnostics, environmental monitoring, food safety, and pharmaceutical analysis. This ability to detect low concentrations of substances in real time make it an essential tool for scientists and researchers. That's all. Thank you.